from the surroundings. Then heat depends on direction, right? Yeah. Q just balances between Q and W, right? And then also ds and dv are exact. It changes with the distance, yeah. And heat depends on many things, right? It's in pressure and volume. I see. From functions that depend on the path taken to reach zero. I see, I see. Q isn't done, right? Q is not. This is dependent on why. Why is thermal? Extensive state. So thermal is extensive, same as extensive is same as like not path dependent, path dependent, non-state. Intensive, which is path independent and state. That makes sense. Perfect. Hey, what's up, man? How are you doing? Can you hear me?
Hello.
Yo, how was your quiz?
It went okay. I think a lot of it was just basically just the stuff from T6 and T7.
Okay. So this quiz, I thought this quiz was like a math quiz. So like that part, I think we talked about T6, and then you said T7 was not bad, yeah.
Yeah, it was just a lot of like turning this equation into that equation and
A lot of algebra.
yeah.
Okay. How much is like how many questions in the quiz do you guys typically get?
4.
And it's 40 minutes?
Yes.
10 minutes? Oh, okay.
Though you have to take a picture of your work and submit it, so that takes a little longer to do.
Oh
So
man.
I usually only get about 35 minutes or so.
Yeah. Did you finish at least though?
Yeah, I did.
Okay. That's good. All right. I guess we don't have to like. Did you finish T7? I guess because you studied it. You've already finished it already, right?
Yeah, the only things that are really left are the exercises. It's been
Oh,
it's been a kind of a messed up schedule this week because of
it's
the
okay.
things that changed around, and
Okay.
it's been.
It's I'm pretty flexible. If we need to cover, or Saturday you said doesn't work
I mean,
for you.
Saturday's okay, but I have 2 Zoom meetings pretty much one after the other. But then other than that, that's it. So Saturday's still okay, but it's just this week was
Yeah.
I really can't do this situation this time around.
Do they usually do they switch it up, or is it something happen?
No,
Like
it was just like I'm not saying anything mean to you or anything, but it was just the change of schedule and everything. I kind of had stuff kind of planned around, and it kind of
okay.
messed stuff up.
Yeah, I have work that's usually, but let's for next week let's do Tuesdays and Thursdays if that works for you, and then
Okay,
Sundays.
Tuesday, Thursday, and Sunday. Okay. Yeah,
Yeah.
if you can do it that way, that'd be great. But otherwise, I don't know if I can. I may need to
Okay.
work with someone else. Maybe I don't know
Okay. We'll
because
keep it that way though. It's I mean these the chemistry stuff. I don't know that the homework for math isn't that bad. We'll talk about that on like Sunday.
okay,
Uh,
yeah. There's a lot of determinants and just really Bronskins, and that's it.
did you start on it? Did you start on it?
No, not yet. But
Okay.
that's from working with a professor. I think it's on Monday. I worked with a
Yeah.
professor, and
Oh,
yeah,
that's good.
it seemed to be okay.
Okay. We'll definitely still go over it. I think it's good for reiteration,
Okay.
just like each individual step. So, for this one, you said you want to talk about the exercise, or did you have like further questions about like the concept, the critical thinking?
Um. Okay. Yeah, because I was just a little confused because stuff. So we're working on PChem this time, right?
Yeah,
Okay.
the
Okay.
T7 stuff. Yeah.
Got it. Okay.
You see my board, right? Like my whiteboard.
Yes.
Okay. I was just wondering if there was questions you had for the CTQ.
Let's see.
I really like this T7 one because I mean besides like there's some concepts here that are really great, like what is independent,
Mhm.
and then what's state.
Yeah. Just kind of wondering relating to the table itself, where you have to construct the table.
Oh, that one. Okay.
Yeah. So
Bottom.
the reason for the delta H and the delta S system,
Yeah,
all
entropy, enthalpy. Yeah.
yeah, entropy and enthalpy. I guess the first one's entropy total, and then enthalpy. I don't know. No, enthalpy total and entropy of the system change.
Yep.
Uh, both of those were equal because of integration,
Okay.
canceling them out to 0.
Yeah. For which these ones, what I usually do, maybe if you guys, because like this one, I usually just look up,
Okay.
this, and then like this, there's an equation that relates the enthalpy to the surrounding one, right? This guy,
Mhm.
right?
Yeah.
You just have to follow that, and then like the total one is pretty much once you have the surrounding, you just add them in the system.
Okay. Because he, it's kind of weird because he ends up basically going over in for the PChem, pretty much going through all the problems, critical thinking questions on T7,
Okay,
pretty much
what did he
all the
do?
other activities. And he ended up getting for the number 14, the delta, I guess the delta H, absolute um, entropy, I guess, or
Yeah.
absolute enthalpy of the, I guess, total or whatever. Um,
Okay.
he ended up getting 6,025 for all three temperatures. So
6,025. Okay, let me take a look at that picture because like that number seems familiar.
okay,
Because I think that number is the one that's given to you, isn't it?
yes.
That's let me. Yeah, this one's a little confusing because like he wants you. You're given temperatures, and then you have to calculate these guys. So I'm thinking like they're gonna change because your temperature changed. Why doesn't it change?
Well, the way he explained it was you basically integrate your delta CP of
Okay.
the reaction dt,
Okay.
and that integral, that delta R, the CP, becomes zero when you
Okay. I
do
see.
the, I think it's probably due to natural logs. That's what I'm guessing. And
Okay. Okay.
that cancels out to zero. And because of that, there's no change in enthalpy,
Okay. I think
no matter how you
I've
change the temperature. So
that
that,
make that makes sense. Okay.
yeah, so that's 6,025. And the same thing with the the entropy of the system. The third table, all three were basically um, the same as delta S surroundings at zero,
Okay.
but without the negative, because the equation is the delta, I think it's delta H over T, I think, the negative.
Yeah.
There's a
Yep.
negative H surroundings over T.
Yeah.
Just that H itself by itself is pretty much the same for all three temperatures. So they're all 22.1.
If they're
Uh,
the same delta H, yeah, that would. If the delta H is the same, then that must mean yeah, because they relate back to the entropy.
okay.
Okay, just go with what he tells you. I had some questions on this guy because
Yeah.
this one right here, I usually what I do is I just look up the CP, and
Mhm.
then for me it changes. But go with what he tells you. Does it make sense?
I mean, for me, it does.
Okay,
I
yeah.
really don't exactly know, but this is all new material, so I just kind of go with it.
Yeah. So just go with that one because it's weird because like the equation for like delta H is this guy. Like
Hmm.
you have this guy right here usually. You make it equal Q, and then you're
Hmm.
not given the mass, and you have T right here, right? This
Yeah.
is like heat capacity. So like this T, is this the T of the water? Like initially, because that's what we had. Like it's initially at like 273 Kelvin.
Yeah, it releases 6,025 joules per mole of energy, I guess. Or
Uh,
I don't
yeah,
know if is enthalpy energy,
kind of. It's not really because
or is
everything.
it heat?
What is energy? Like there's a lot of energy. Like thermal.
Yeah.
Like enthalpy is in a way it's like when you have like delta H as like greater than zero. This
Hmm.
kind of tells you um like if this is endothermic, right? And then for the
Yeah.
most part, like if delta H is like less than zero, this is like exothermic, something like that.
Hmm.
So it is related to heat. Like it's related to
Okay.
heat for the most part. And then S is the one that's hard to
Yeah.
grasp.
Hmm.
But like there's a relationship between like enthalpy and then entropy.
Right.
So like if you're talking about let me like go back to this guy. Like this tells you like if delta H is if it's positive or negative, it tells you if heat is being absorbed, right? That's what it
Hmm.
tells you. So being absorbed means like
Yeah.
endothermic.
And I think also in the problem itself, you make the assumption that delta RCP is zero.
Yep.
So that really kind of cancels out a lot of things and makes it more simple.
Yep. Yeah, it's really not that bad. How do you like these kinds? Like, do you understand like why some of the assumptions you make that for some of these like there's Gibbs. I know we didn't really touch on Gibbs yet, like officially, but like at the when you transition, like when you're going from solid to liquid.
Yeah, it requires a lot of like heat or energy
Yeah,
too.
but at that point, that's where you get equilibrium. Your Gibbs is zero there, Eh, and that's why you're able to make this go to zero. And this is the Gibbs equation. So Uh, and then this is that equation, I guess, like the one with the natural log that he's talking about that cancels out.
Yeah, the cancellation. Yeah. So
What about
yeah.
these other ones? Did you have other questions about like these other ones?
Hmm.
These derivations, I think they're very typical. I think you might see them again. You know how like all the derivations here are very good, where you have this entropy as like a function of temperature and volume,
Hmm.
and then you get like some weird partial differential equation.
Yeah.
That is a pretty common one. Like how to derive those. We're gonna get to like I don't know if this class goes to like Maxwell's equations, but in the end like you're gonna all these are part of that.
I mean
Uh,
that we touched on that in all the way at the beginning with Maxwell distribution of molecular speeds.
yep. Yeah.
As you increase the speed of the molecule, the lower temperature molecules will end up decreasing. So less and less molecules move at that speed at lower temperatures when there's higher. So it's like the higher speeds of
Okay.
molecule, less of those molecules are at that rate at
Okay.
lower temperature, but at a higher temperature, um, it does the same as well. So
I think I remember talking about that like what is an ideal you know gas? I think it's like
mhm,
when low pressure and then there's like a limit.
yeah.
Okay. Are you good with like knowing what something if something is state or path dependent? The difference between those two?
Could you kind of explain a little bit more on that? Because
Okay,
path
okay.
path is like
So there's
state.
one here and then there's two here. Okay. I'll
Mhm.
talk about it. It's this is the one I like this I always find some interest in talking about because like when you're saying this is all equivalent. Is it an extensive parameter? Is it path dependent? Is it non is it not a state variable, you know?
Mhm.
That's all the same. And then if something is path dependent, then you can't really, like it's not just taking its like initial and final. And like, there's two things typically in thermodynamics that are path dependent. It's going to be your small, and they're usually small letters. It's going to be your Q and then W, the work and thermal, right? Thermal
Right.
energy. So mechanical or work, and then this one's thermal. And they're lowercase, that's the convention. And then the reason why that is like work changes with distance. This is that force thing, right? Force and
Yeah.
distance. And then so this other guy, the heat, it's gonna change, right? Depending on like you're warming up, if you're leaving the system or like you're going. So depending on where you start, that's gonna change. It's not gonna be constant. But this guy, like whatever, like these are all the big letters. So you have U, like even though U is like composed of like path dependent variables, like this eternal energy, even though it's like Q and then W here is path dependent, they will really since it's an equation, and this is equal this guy, they will balance itself. They like Q balances with like W, and this compensate, and this becomes a state. It becomes a state variable.
So
Internal energy,
state
yeah.
variable, is that the same as matter states, or is that a different form of state?
Like define that like state of matter.
Like
What do you mean?
state of matter, like solid, liquid, gas, plasma,
Oh, I see what you're saying.
point, Bose-Einstein condensate.
Yeah, that one. That's like a trend. Those are like it's not
And
really that. It's more of
transition
like
states, I know, are there,
it.
but
That's why I don't call it state. Like it's just there's different names. It's not really like liquid state to like that's a transition state. That's
okay,
different.
so I guess phase then.
Yeah, but this state means like is it path dependent, and state means it's path independent.
Okay, so
Uh,
path dependent is based
Is not
on an equation, or what
path.
is
What does
exactly?
it mean? Okay, what is it? So path dependence means that like it is like when you're trying to do this guy, which is like W, right?
Mm-hmm.
It depends on this equation. This will change, right? And then, like, if you change like how far you're going, pushing this guy, your work is gonna either increase or decrease.
Mm-hmm.
So that's the equation for like why it's a path dependent. One of the variables, force will change as well, magnitude of force. For this guy though, if you're talking about like entropy, and then like you're talking about volume, volume itself is not going to change depending either you're in like solid or liquid, right, or gas.
Okay, so there's basically, it's just the relationships between them. So like it's similar to, like, I guess you just mentioned, I just didn't quite catch it, independent and dependent variables.
Yeah, if we're talking about state, it's path independent. It only depends on the final and initial state. It doesn't depend on what path you take. So state variables are only dependent on the final and ending, initial and or final and initial, like parameters, but they're not dependent on how you get there. But for path dependent or non-state variables, these will depend on like the distance. Obviously, like you can take point A and point B, you can take different routes to get there, right?
Yeah.
And then the distance is going to be different depending on your path.
That
But
sounds a little more familiar.
And then this guy, it doesn't really matter what path you take. It just depends on A and B, these variables. So this can be like your initial, this can be like your final. And then in the end, it doesn't matter what happens in the middle or the path. That's usually how it's explained. But for me, the way I look at it is, it will not change. Like it will always be the same. It will just like depend whatever path you take. But for the most part, if someone asks you, give me like a path dependent ones, it will just be Q and W, heat and work.
It's path dependent. So does that mean it's basically kind of like you don't just focus on the overall change, you have to look at all of the interactions going on, how you get there. Okay, so that's dependent, and independent is like temperature.
And temperature itself is it's also a state. It's a state variable. It's only dependent on your final minus your initial, right?
Mm-hmm. So can a variable be both path dependent and independent depending on its condition?
It has to be either one. Like when you say, I mean, if you're gonna say it's path dependent, maybe in one instance it's path independent, but it's always you don't consider it like a state because it's path dependent in other times.
Okay, so basically a state function can either be independent or dependent of path, but a non-state is always dependent.
Yeah, I wouldn't call it that way. I wouldn't like see it, like define it that way. I would just separately say this guy is dependent and this guy is independent. I don't think there's one that's like both. I've never heard of that one.
Okay, because like I was thinking like temperature could be both independent and dependent if you look at DT versus temperature at a certain time, like measuring times independently of each other.
Conceptually, yeah, like a lot of these like conceptual, but the definitive like rule is, it's usually just like the definitive rule really is these two are the ones. There are like density. What about density? What do you think density is?
Well, density is,
and remember, volume is state.
I still don't understand the difference between a state and a non-state and how that's different from dependent and independent path.
It's the same thing. Like state, like I said, state is path independent because it doesn't change.
And a non-state is path dependent.
Yeah, that's equivalent. Yeah. That's
okay, equivalent. So they're just two ways of saying the same thing.
And there's a third way too. There's actually a third way. Like the non-state path dependent is called also an extensive variable.
So path dependent non-state is extensive, Um,
and and then the state path independent is the same as saying intensive.
path independent.
Yeah, path independent is the same as state, and then path independent is also the same as intensive.
Okay, so it's path independent state is intensive.
Yeah, just like have that all equal each other. Like when you're building up all this definition in your mind, those are all the same.
Okay, so non-state is path dependent or extensive, and then state is path independent or intensive.
Yeah.
Okay.
And so like when you apply that, you're looking at this thermal identity whatever equation 4, you already know, right, which one is independent. And then it's only asking for exact differential. You could say temperature is one of them, but it's not a differential.
Mm-hmm.
Yeah, a lot of these are conceptual. That's why I wish I'm just like doing the exercises, because those are like qualitative ones. A lot of this is like math, like a lot of just derivations, and maybe the only one that's not is the table one.
Mm-hmm.
Let me look at this one. Check the next one. Let's see. Did you get number 11? And then actually see your solutions for these. Did you do 11 correctly?
So what I said was, if what we went over is on number 11, if temperature increases,
Yeah,
your
that one.
final temperature will be greater than your initial temperature,
Yep. Okay.
which your natural log will be non-zero. Um, and then your delta R of, I guess, entropy of T2 minus your delta R of entropy of T1 will be greater than zero.
Okay.
If your delta R CP is greater than zero.
So what is your conclusion there? Like what can you say about
So
delta
I
S?
say delta S will increase because there's a positive difference.
And what was the solution like the professor had? I just want to
Um,
know.
yeah, I think if he didn't make a mistake, that's pretty much it. It's just basically he went over this in class. Let me see,
Okay.
because he also sent official
Okay.
solutions too. So I'm
Oh,
just gonna
perfect.
pull that up
Yeah.
real quick. For
This one,
number
this one
11,
isn't. Yeah, this one isn't bad. I just wanted to know because usually a lot like this one is very conceptual. Like you can,
yeah,
and then it doesn't give you what if it's raised. How is it being raised? Is it raised high? Is it raised like 1 degree?
yeah. Let me just pull up the thing real quick to share screen.
This is kind of like what's it called? This is kind of like a GRE question. One of those, it doesn't give you. It gives you relative values.
Yeah, let me see here. So, here it is. Sure. Okay, so that's pretty much it. It was super short.
No. If possible. So he's saying it's gonna increase. That's what he's saying.
Hmm.
That's weird. Like, what if it's increasing like just a little bit? The natural log is less than that though. You
Yeah,
know,
but
and
like the idea is that T2 will still be larger than T1, even if it's just a little bit, and so it would still be non-zero.
but say this is but it's saying does delta R increase, decrease, stay the same, or is it impossible? Because what I did in minds is like, okay, we'll go with what he says. I'm just trying to explain like, what if it
Yeah.
increased like 1 degree, right?
Hmm.
And let me just show what I did. All right. What if it increased like 1 degree? Increase 1 degree, and then you do the natural log. It's obviously it's gonna be less than 1.
Yeah, I'll just probably, because tomorrow's Friday. Okay, so trying to think. I'll ask him about
Do
that.
you understand what he why it's increasing though? Like,
Yeah,
I,
but I mean,
can you
because
convince yourself this?
it says in general, when the temperature is higher, it doesn't necessarily say, it says greater than zero. So I'm guessing that you can look at any possible number greater than zero. So like, so T2 can be, let's say, it could be 1,000,000 degrees more than T1, or as little as,
Which means if
degrees.
it is if it is high like that, then it is increasing. If
Mhm.
you're saying it is increasing like very high, but if
Yeah,
it's like
that's,
only 1 degree, it's less than one, so it's like a fraction of like of this guy.
what do you mean? Because if it's by one, it's not a fraction of one.
No, it's this guy is a decimal. Once you do this one like this, the ln of 21 over 20
Hmm.
is less than one. And if it's less than one, it's a fraction. It's not this guy.
Yeah, I think it also says consider a pressure process in which the RCP does not depend on temperature.
It's not this isn't depending on temperature. That's why it's this guy. There's another equation. This is constant right here. This is constant, right? CP. Because like that's how you apply this equation. This right here is a constant value. It's not dependent on T. That's why you're able to take it out. That's why it means.
Hmm.
That's what it means. Like when it's constant pressure from the previous, from the was it number 10? When you derive this equation here, since your CP is not dependent on temperature, you can take it out of the integral, and that's how you got this actual equation. By
Hmm.
the way, like yeah, just ask him how he derived that one. Because I still think that it's depending on temperature, so you can't even determine it. It depends on how much is being raised,
Hmm.
but doesn't matter though. Let's look at. I think all these other ones are pretty general. I think that was just one where like, oh, okay, it could be one or the other. What about this one? The which one is it? Number 8B.
8B. So I don't know. I just put I just said it was applicable to an ideal gas, but that was it.
What did he put?
Let me see, B. 8B.
What I put is like that CP. I mean, it's constant for ideal gas. Yeah.
Yeah, he just said the expression is generally valid at constant pressure.
Yeah, that's what I put. It's valid at constant for ideal gas, but it's variable for real gases.
Hmm. Hmm.
Because you can't, if you're using real gas, this is gonna be, you can't apply that equation where you have like iso, you can make one like pressure constant and get a C, and then make volume constant, you get a C.
Yeah, it's just with these problems and things, I I understand why it's happening,
But
but I don't know, like I guess I can't think in that terminology.
like the way he concludes it, the way he concludes it.
Well, yeah, but also in general with I guess how people explain it, like
Over
it
time,
doesn't
yeah, I see what
just
you're saying.
doesn't make sense. It
Over
makes sense,
time,
but it doesn't make sense.
no, I know. Over time, since this is your, I guess this is your first thermal class, right?
Yes.
Yeah, like it's the same with anything. Like if you're taking, there's a lot of chemistry you've taken probably a lot of times. Chemistry just evolves, and then the actual generality is thermo, and then over time, the more you run into these terms, and then you see like kind of like the ending and the because like they're just gonna get more general. You start with ideal gas, and then you work with real gas, and once you know like the full spectrum. Right now, it's like limited. Like you're pretty much just assuming stuff. So over time, the best way I can say is really know your definitions. You know, like what is
I don't know
what is
that part.
what is entropy? You know, what is enthalpy? Like, and then the other thing is after you know your definitions, it's like know qualitative like factors. What increases enthalpy? What decreases enthalpy? Right? Like that kind of stuff. Like what if something is like greater than, like if S is greater than 0, what does that mean? We talked about that one, right? That's like irreversible.
Oh, okay, I forgot.
It's those things. Like a lot of times, that's why like he's probably asking you guys to do this like critical thinking questions, because this is what's gonna linger. It's not you know, when you're out there in the field, like it's not about like that. Can you solve like a problem? Like it's more like the behavior, and that's when you make these assumptions. Like after you make these assumptions, then you can move forward with like an experiment, something like that. But like
I don't
it's kind of
know.
making sense. Is it somewhat making sense? Like the derivation of the equations, though. Like each equation that you derive, does it have like some
I mean,
sense?
yeah, but like don't I don't like whenever it comes to connecting something from a previous section,
Yeah.
that's what I don't know. I look at it a lot, but it's like it doesn't want to come together.
But so like the first law. Do you remember we worked with the first law? That was like the previous one, right? And then the second law. Second law is just pretty much putting that together in the there. It's just all equations. The second law is just this equation. You know, the differential version of it, and then you have this du guy, or you know, du equals like dq plus dw. That's the first law, differential. And then like, you know, I mean the enthalpy or entropy, you have this dq equals tds, right? And then you plug this in here. And then like if you look at this equation, this is how I would assess it. So you have like, if you increase T, your temperature, right? What happens to your heat capacity? It goes up, right?
Yeah, it goes up.
And that's how I would like look at it, like, and then like convince yourself like, okay, that makes sense. And then if your entropy increases, constant T, at constant T, what happens to your heat? It goes up as well, right?
Yeah.
That makes sense. So, but then what about this guy? You know, you increase your entropy, or like hold on, what about like let's just talk about this one. dq over t. This guy, if this goes up, this goes down, right? Does that make sense? Increasing your temperature makes
Yes.
your entropy go down.
Mm-hmm.
So yeah, I mean that's how I would look at, like, you look at the equation and then
Okay.
kind of go back to the definitions.
Yeah, I'll do that for sure.
Yeah, like right now, like you probably did like physics 1. Does that make sense? Like F equals ma.
Yes.
And then you did so many of those problems, and it's stuck in your head why, you know, like force equals like 0, and then same with this. It's all just equations, and the equations kind of inform the theory.
Yeah, it's just that they don't really give a lot of problems. It's mainly just
Conceptual.
conceptual information before they move on to the next concept, which it doesn't allow me like an ability to really understand and
I
apply
know.
the things.
I think that what's good is probably if we do like the exercises, you know,
Okay.
the exercises. I mean, I'll just read them off right here, like, and kind of like talk about. We can probably. The thing is like it's so many problems because if I do like the critical thinking,
Mm-hmm.
and then I also what if I can you handle just the critical thinking and I'll do the exercises, because then
Yeah.
like. Because in my
Yeah.
mind, like if I do the exercises and I kind of like explain it to you, and then at least there's like some traction. Because the exercises, this is where all the concrete numbers are. There's no, like for example, this first one, I'm looking at T7 right now. It says here, what is the entropy change if 1 mole of liquid water is heated, right?
Right.
From 0 degrees Celsius to 100 degree under constant pressure. I'm seeing like an equation there, and then it gives you the CP over this temperature interval. And I think you have you have an equation that relates that one. So I would just find an equation, and then like relate it back to that and solve for it.
Okay, that would be the natural log one, right?
Yeah.
Okay. And also, is there a difference between a bar CP versus a non-bar CP? Or just
No,
bar
no,
versus non-bar?
it's pretty much the same thing. The reason why you're doing that is it's a constant. They're saying it's a constant.
Okay, because I've also heard it's an average.
Is that what they said?
Well, I know like all the way at the beginning when they were going over, there was a different equation where it was showing, I think it was with gases, where they
Okay.
used a V bar, and
Okay.
V bar contained the
Oh, I see.
averages of
I
all
see.
the.
I see. I see what you're
How do
saying.
you know which one is going to be the right definition for the case?
So, say that again. What does that mean?
Like, how do you know when V bar or just a barred variable is related to averages versus just
The
like
regular.
regular?
Okay. I see. I think let me recall. Have you done? Because I've done this. Like, I could probably show you how I did it. But have you tried calculating CP from like products and reactants? Have you done something like that?
No.
Like you're given like a chemical formula and then you have to calculate like CP.
Yeah, we never done anything like that before.
So like this bar usually comes in at specific heats, CV or CP, and then they technically change. That's why like it depends on like I remember it depends on because like it changes depending on like your moles, on the chemical formula. So anyways, if they say like CP bar, I would just use that as if it's a constant. Like run through the equation as if it's a constant, like the same equation that you've been applying.
Okay.
There's no different equation for like the average,
Mhm.
like
Yeah, then I've also seen almost similar looking to absolute value bars, but they're used in a different way.
yeah,
So,
probably like magnitude. I don't know, like absolute
okay.
value bars. Yeah,
So like when you're doing with vectors,
yeah, those are like magnitudes.
magnitudes, okay.
Like usually when you put them like a vector inside like absolute value bars, that's like just the magnitude, which is just the square root of the squares of its components, whatever.
Yeah. Okay.
Yeah, like so maybe I should do this. I feel like we need more like concrete exercises,
Yes.
and then just
That would
like,
be.
but then like I have to like partition it. Like maybe for this T8 one, do you want me to just do the exercises?
I mean, yeah, like, and I'll just, I may ask a question or two off of the critical thinking and you can kind of take a look at it if I have any questions. But
Okay.
yeah,
When's your exam for this next one?
the exam, let me pull up the schedule again.
Okay, because the main like high level points is probably doing the exercises for first law and second law. I think like T6, T7 is a good one.
Okay,
And then
exam 2 is going to be the 14th. So,
okay, we have a lot of time. Okay.
yeah.
So from now on, I'll do for the T8 one. I'm not even gonna do T8 critical. I'm just gonna do the exercises.
Okay, yeah, especially because he really goes over critical thinking questions in class.
But he never goes over the exercises, right?
Never goes over the exercises, yeah. Except for one, which was, if I think I sent you the T8 already, yeah, through text. That one he did go over like a critical thinking type question, which was number 1, which was like showing how to calculate absolute entropy of nitrogen gas at standard temperature and pressure.
Yeah, yeah.
That's a big
There are some some exercises that kind of look like a critical thinking. Like there's So yeah, I mean, in essence, what I'm saying is he doesn't even give you the solutions for them, right? He doesn't give you solutions for exercises. It's only the critical thinking. So,
Well, yeah. I mean,
so
he
like
just does.
if I do them, at least you'll have like the full package to like study for the exam.
Yes, that would be good.
Yeah, and I feel like that's kind of like maybe you can tell me like because for me it was like that as well. Like the well, when I was doing mechanics, physics one, and then like electromagnetism, all that, and then this thermodynamics, like it doesn't really like add up until the numbers come in, the physical numbers, you know.
Hmm. Yeah.
And then the more you do them, because that's the different. Is this book like something he wrote by chance? It looks like some, or is this like just a? It doesn't look like a
Yes.
textbook.
Yeah, this is actually what it was based on.
I see. I see. Okay.
Yeah. So it's just like they just ripped a bunch of things from that textbook and put it in and slapped it as a custom edition with Wiley. So
Okay. It's fine. It's just yeah, like because like the critical question ones is like I was like, oh, okay. Is it's not bad. Like let's do the exercises and see if you like it.
okay.
Uh, so I'll send you that. Probably I'll start on it today. And then what? Oh no, I'm on. I guess so. We're not gonna do Saturday, right? We're not doing Saturday, or did you want to do Saturday?
Well, Saturday probably not, just because I think we're okay when it comes to the chem material. Yeah, and I'm
Okay.
also kind of, because I'm actually finishing up a lab report that's due tonight.
Yeah.
But
Go ahead and do that.
it's been a really bad week for me.
No, no, man. Like
So I
I
need
think.
some extra time to do stuff. And
Yeah,
the
I know,
videos and everything.
I know what you mean. Yeah, definitely. Let's just meet on Sunday. And then, did you want to just talk about homework 5? Because it's due on Sunday, right?
Yeah, I mean, it's like a 8 question homework, I think, or something. It's
Okay.
not too
I'll.
long.
I'm gonna send that to you earlier than Sunday, so that you can take a look at it. Uh,
Awesome.
so I'll do that, and then like so like then the T8 stuff is due on Tuesday, right?
Hmm.
So I'll send that to you, but we can talk about it if I get to it, like the exercises
Okay.
and like homework 5. And I think that should be it, unless you guys have like if you have any questions.
Yeah. Let's see. Yeah, definitely. If I have questions, I'll let you know.
Yeah, because this wasn't that bad. Like when I was
Yeah,
trying to do this.
they're
Oh yeah.
shorter too than they used to be. Like some of the earlier things were really long. The
Oh
gases.
really?
Yeah, gases. So there's how many pages here? So went G1 went from 19 to 29, and then G1A
Wow.
was 29 to 39, uh,
Wow.
and then I mean G2 was 42 to 57. So much longer than these. These are shorter.
That's good. I mean, as long as okay. So like for this one did you want to do this? I forget at what time. Is it 6 to 8 for Sunday?
Yes, yes,
Okay.
6 to 8.
Okay. I'll just yeah. We can talk more during that time. And today I had like such a long day as well. So.
Oh man, yeah. Also, it's the first of it's like third
October.
quarter, so it's like
Yeah.
just having to. I was like working on like what I purchased and everything, and like I had a lot of like accounting to do to figure out like budgeting and things. So it took a long time, and I get
Yeah.
tons of emails all the time, so I just had to go through all those, and
Yeah.
it was a big mess, hot garbage.
Yeah, I know what you mean. So like for you have 3 classes, right? Like, and then is
Yes.
that spans like all week, or do you have like a free day?
So on for my mainly it's Tuesday and Thursdays that are the most free, but um, just point out my schedule here. It's pretty much first half of the week, even though Tuesday is pretty empty. The first half of the week is preparing for the lab. on Wednesday,
Oh,
and
you guys have a
then
lab. I see.
and
How
then
long
we
are the
should
lab?
join.
Like for this class? How long is the lab? Usually it's long, right?
Yeah, so I went to two for the past 2 weeks. I went to two in-person labs that went from
I figured, yeah. You can't really do this like
three,
in online.
yeah, from three to I think 3 to 6,
Yeah.
at least 3 to 5:30 to 6 o'clock. So that's a good two. But actually, no, it was from 3:30 because for some reason they start lab at 3:30, not 3. So 3:30 to 6
Yeah.
usually.
Yeah, the professor or is it like a TA teaching it or
So before that, from like 2 to 3:15, or I mean 2 to 3:30, it's a lecture. Um,
I see.
and he
Yeah,
usually talks a long time, and then
I
the
figured.
TA, who's kind of a heavy on time, kind of bratty, a little bit bossy, comes in and just
It sits
waits
there
for him to be
to
done.
finish.
Yeah, and then he's like, oh, okay, I guess we're done. So
That's
he
funny.
can
That's
just
funny.
talk. He can just keep talking. He's great, but you know,
Just does he like this is his major, I'm guessing, right? Like he has like a PhD in like is it or in
yeah, yeah.
physics or something. I don't know. Is he an engineering professor?
He is just a PChem professor.
Oh, PChem, I see. Okay, yeah. A lot of my professors like usually like yeah the especially like these very rigid topics, not really that talkative. I find it funny sometimes like yeah they can yeah it's interesting. It's more of like a natural science one, you know. But
He has a
does it
DSC degree, so I don't
uh,
know what DSC is. Doctorate of
BS oh Doctor of Science? It's the same
Doctor of
as a
Science.
PhD.
Okay.
He probably got that in like some other country. Like
Yeah.
usually it's like another country. But like does it give you guys a lot of like there's this video like this professor online I always watch like it's not bad, it's not bad, but like you know how you have a professor and then he's like, oh, I'm not gonna talk about anything from the textbook. He says that like that's his like disclaimer, and then but what he will talk about is like everything like applications from like for physics or chemistry. Is it kind of like that? Like does he talk about the applications? That's why he's talking so much.
He doesn't actually do any videos. He just works through these problems. That's it.
Oh, he works through the problems. I see. Okay, but
Yeah,
then
he,
does
he
he
doesn't do any
is
lectures
is
at
he
all.
is he very descriptive? Does he explain like each step? 'Cause a lot of professors sometimes they don't like they miss a step, they skip steps, or is he really good about it? Like explaining
He
all his.
most likely explains things, but he just kind of goes fast. So he just kind of covers a lot of topics quickly.
Okay,
So
I see. Okay, all right, man. I'll see you on Sunday then.
alrighty.
I
Thank you
think this
so
was good.
much.
Yeah, sorry about this week. We'll definitely like go back to the routine next week.
Okay.
Okay,
That would be
cool.
great.
Have a good one. Have a good
You
night.
too. You too.